Hello, my name is Bridget Kimsey, and I'm the mentor for our team Architecting AI for Space Travel. I'm a PhD student in AI and NASA JPL Solar System Ambassador. AI is a complex, layered, and multifaceted field moving eventually through every industry. Our NASA Seas team has been researching and creating ideas on specific areas in AI as it relates to space travel. Our six-member team will now briefly talk about their research and ideas. Nikhil will begin us off.
Hi everyone, I'm Nikhil Krishna. I'm a rising senior at Thomas Jefferson High School for Science and Technology, and I'm from Ashburn, Virginia. As we look into the future of artificial intelligence in space, I wanted to really hone in on what is hindering its development. Currently, artificial intelligence in space is limited to simple algorithms. A big reason for this is due to solar radiation. This is because it can cause overheating issues along with bit flips of AI chips, leading to unreliable or dangerous outcomes. This creates major concerns with regards to the reliability of AI in space. To narrow the scope of the problem, I wanted to focus on CubeSats, which are miniature satellites which are standardized in size at 10 centimeter by 10 centimeter by 10 centimeters, as you can see in the image in the bottom left. Unlike other satellites, CubeSats often have weight limits when launching, and thus the bulky and heavy radiation shielding that is typically used on satellites is not viable for CubeSats. Next slide. My proposed solution takes from the biological life form known as the Saharan silver ant. These ants have ultra-refractive hairs, which they use to reflect sunlight to keep themselves cool. In the image of the ant in the top right, you can see how reflective their surface is. These hairs use a triangular prism-like structure, as you can see in the image in the bottom right, which allows for total internal reflection, which is when light traveling through a medium is completely reflected out. Using this technique, I propose to mimic this strategy by using a silicon-based polymer film with triangular prism microstructures on its surface. The material is called PDMS and has been proven to have two important properties. First, like the Saharan silver ants, it can reflect UV radiation and visible light with an approximate reflectivity of 95%, which reduces the amount of solar radiation absorbed. Second is that it has a high emissivity in the mid-infrared range, which means it can radiate internal heat from hardware components, effectively acting as a heat dump. This film would be extremely lightweight and would only need to have a maximum of 5 millimeters of thickness. The film would be applied to the outer surface of the CubeSat where it could dump the internal heat into the cold sink that is space. While this needs to be further tested in space-related conditions, I believe this is potentially a step forward to unlocking the vast benefits of using AI in space. Overall, I've had an extremely enjoyable experience working as a NASA Seas intern, and I'm beyond thankful for the opportunity and to my mentor, Ms. Bridget Kimsey, and fellow interns as well.
Thank you so much, Nikhil. We are now moving on to Nidhi's work.
Hello, my name is Nidhi Kumar, and I'm a rising junior at Clements High School in Sugar Land, Texas, interested in artificial intelligence and its role in both Earth and space. AI has a wide range of applications, one of them being its ability to predict deforestation. On the left side of the slide, there are two satellite images comparing a forest area in Colombia from 2000 to 2017. Using similar satellite images, as well as drones and ground reports, AI is able to accurately predict where deforestation can occur. For example, researchers at Westcliff University developed a machine learning model that uses supervised learning and neural networks to pinpoint critical deforestation hotspots with an accuracy exceeding 85% in some areas. Compared to traditional models, AI approaches are often more accurate, cost-effective, and faster, helping governments and conservation groups prioritize areas for protection and resource allocation. Next slide, please. But what does this have to do with space? First, maintaining a healthy Earth is essential for the future of space exploration. Our planet currently serves as the only launch pad for rockets, satellites, and other spacecraft. Without a stable environment here, advancements in space become nearly impossible. Also, similar technologies that model Earth's ecosystems can be adapted for space. The Dynamic Meteorology Laboratory in France has developed a non-AI tool called Dynamico to stimulate atmospheric circulation. In addition to modeling Earth's climate, this tool is also being used to study Mars's and Venus's climates. And fun fact, research into Mars's weather patterns has improved our own understanding of monsoons here on Earth. While this has not been fully explored, I hypothesize that we can use transfer learning to adapt Earth-based deforestation models to studying planetary climate change. Transfer learning is a machine learning technique where knowledge gained from one task is applied to a different but related task. For instance, the neural networks trained to recognize environmental degradation patterns on Earth could be fine-tuned with atmospheric or surface imagery from Mars, Venus, or other celestial bodies. This approach could help identify geological changes, map dust storms, or monitor ice cap fluctuations in these extraterrestrial environments. Overall, I really enjoyed doing this project, and I'm very grateful to NASA Seas, Ms. Bridget Kimsey, and my other interns. Thank you.
Thank you so much. We're moving on now to Didi's work.
Hello, I am Didi Obamanu, a sophomore at Stratford High School from Texas, interested in research which focuses on addressing the environmental effects of increasing space travel. The growing carbon and pollution costs from space travel is a serious environmental challenge. Rocket launches release black carbon and other pollutants into the upper atmosphere, contributing to climate change and ozone damage. How can we use AI to track and address this issue? Green AI uses energy-efficient artificial intelligence to reduce power use and carbon emissions while still providing accurate analysis. This is different from red AI, which ignores energy use and adds high carbon costs during training. Satellites like Sentinel-5P and NASA's Ozone Monitoring Instrument, OMI, collect daily global data on greenhouse gases such as nitrogen dioxide, carbon dioxide, and methane. This data helps track pollution from rocket launches, providing essential information for climate monitoring. Next slide, please. Using green AI to process satellite data makes it possible to detect pollution hotspots, track emission trends, and predict future pollution levels effectively while keeping the analysis itself environmentally friendly. This helps support targeted climate actions and policy decisions while monitoring and reducing the environmental impacts of space travel and pollution. With further application in the field, integrating green AI with satellite monitoring remains a promising approach to supporting climate goals while managing the environmental impacts of space travel and pollution. In conclusion, green AI, satellite data, is a powerful way to reduce negative impacts of space travel. Thank you to NASA Seas and my mentor, Ms. Bridget Kimsey, for providing the resources, mentorship, and data that made this research possible.
Thank you so much, Didi. We are now on to Sandy's work.
Hello, my name is Sandy Shanmuganathan, and I'm a rising senior at Portola High School in Irvine, California, with an interest in astrophysics. Today, I will discuss the applications of AI in the study of exoplanets, as well as the search for habitable worlds and life beyond Earth. Exoplanets, or planets outside of our solar system, are a growing area of study in astrophysics, especially as spacecraft such as the James Webb Space Telescope make groundbreaking spectroscopic observations. The detection and classification of exoplanets is a rigorous and data-intensive process. Before the use of AI in this field, confirming an exoplanet could take several years, as data had to be processed manually by humans. Now, AI accelerates this process by rapidly processing large datasets to locate exoplanet signals. Future work aims to use AI not only for detection, but also to assess exoplanet habitability. Next slide, please. Current work integrating AI into this field of study lies in the atmospheric characterization of exoplanets. As mentioned earlier, using AI provides the advantage of automated data analysis, saving time and resources for scientists. In the study The Clear Sky Corridor, the scientists explain that AI enabled the study of exoplanets on a scale not achievable by humans alone. Using an AI-based survey, they discovered a clear sky corridor, a pattern in aerosol formation in exoplanets that likely would have been overlooked without AI, due to the large amount of resources and data required to reveal it. This is a direct example of how AI can be used to study exoplanets with greater speed and precision. Additionally, AI's ability to efficiently identify the most promising exoplanet candidates allows scientists to allocate valuable observation time and resources more effectively. Next slide, please. Ultimately, studying exoplanets not only supports the search for habitable worlds and extraterrestrial life, but also deepens our understanding of Earth and the solar system's evolution. As AI takes on a larger role in exoplanet research, it is essential to understand how the AI arrives at its conclusions about a planet's habitability, so that scientists remain informed and can apply those insights across planetary science. Interpretable or explainable AI models, also known as XAI, are being developed to provide transparency in AI decision-making, addressing the current lack of clarity in how some models reach their conclusions. To summarize, by architecting AI to detect, analyze, and interpret exoplanetary data, we are not only accelerating the search for habitable worlds, but also building the foundation for informed, purposeful human space travel. Thank you to NASA Seas for the opportunity to work with such amazing people, to Ms. Bridget Kimsey for your guidance, and to everyone here for listening.
Thank you so much. We are now moving on to Andreas and Brody and their work in quantum computing.
Hi everyone, my name is Andres Sosto, and today I want to talk a little bit about hybrid quantum classical AI for spacecraft trajectory prediction. Before I explain this model and the results, I want to give some context. Artificial intelligence is already used in space today. For example, NASA's Mars rover uses AI to navigate terrain, avoid rocks, and make some decisions without waiting for Earth instructions. But here's the problem. All of this is based on classical AI, which runs on normal computer chips, and classical AI has limits. Why? Well, because space has harsh conditions, limited power, limited memory, radiation risks, and much more. So I asked, what if we can make an AI model that's smarter and smaller and handle chaotic patterns better by adding quantum computing to the mix? That's where hybrid the model kicks in. What is this hybrid model? This hybrid quantum classical model is a system that combines the strengths of quantum computing and classical normal computing to solve problems more efficiently. So to test out its capabilities, I programmed two models to predict spacecraft trajectories. First, I programmed a classical neural network. Second, the hybrid quantum classical neural network. Inside the quantum layer, we encode data by rotating the qubits with RY gates, entangle them using CNOT gates, and apply trainable rotations. This quantum layer acts like a very powerful pattern detector, which is basically able to model nonlinear chaotic relationships more efficiently than classical neurons. To test these models, I first needed data, so I built a synthetic orbit data generator that creates a 2D elliptical orbit path. I trained both models on 1,000 data points with an 80-20 training validation split, and then I used a mean squared error as a loss function and Atom as the optimizer over 100 epochs. Now, next slide. As you can see, this is how the model would look like. We have the quantum layers and the classical layers combined into one singular model. Next slide. Now, looking at the model results, both had similar validation loss, but when I looked deeper at the average prediction error over the next 50 points, things got interesting. The hybrid model had a 57.95% error reduction, meaning on average, the hybrid model made predictions more than twice as accurately. Even more importantly, the hybrid model only used 326 parameters. That's a 94.21% reduction in model size. So the hybrid model is not only more accurate, it's dramatically smaller. Next slide. This is how the graphs would look like. And as you can see, at the top left, we have the complete orbit trajectory. At the top right, we have the training progress, loss over epochs. The bottom left has the trajectory predictions, and the bottom right has a prediction error over time. Why could this transform space missions? Well, this is where the exciting part comes in. In space, we care about autonomy, the ability of spacecraft to make decisions without Earth, efficiency, using minimal power and computing resources, robustness, handling noisy, chaotic, unpredictable environments, and all of this, the hybrid model reaches this goal even more efficiently than a classical AI. Overall, this internship opened my eyes to look deeper into solutions and not to conform with current technology, and instead use future game-changing technologies. I am forever grateful for this opportunity, and thank you to my mentor, Ms. Bridget Kimsey, as well as my group members. Thank you.
Thank you so much. And now we have Brody coming in again on quantum computing.
Imagine a mission to Mars, a crew isolated for months, millions of kilometers from Earth. Every life support calculation, navigation correction, or equipment failure could mean the difference between life and death. In these unforgiving environments, we need not just advanced technology, but technology that is ethical, reliable, and human-centered. This is where hybrid quantum AI becomes necessary. My name is Brody Ramirez, and I'm a rising senior at Westbrook High School in Texas, interested in becoming an astronaut, and I collaborated with Andres over the topic of AI quantum computing. As he described the logic using his models, I will add on with the ethics and crystallize our idea and the potential of this innovation. With our combined findings, hybrid quantum AI systems blend the power of classical artificial intelligence with the cutting-edge capabilities of quantum computing. This approach doesn't just promise raw speed, it offers smarter decision-making. Quantum modules can analyze vast mission variables in real time. This predicts solar storms that can endanger the crew, optimizing fuel use to extend mission range, and simulating complex equipment failures before they even happen. All while the classical AI core can remain interpretable and auditable, keeping astronauts and mission control in command. Additionally, hybrid quantum AI, when at its fullest potential, can reduce inequality in space science. Fully quantum systems may remain the privilege of the wealthiest nations and corporations, but hybrid models are far more feasible for universities, emerging space agencies, and international collaborations. They help democratize access to exploration, ensuring that the benefits of space aren't monopolized by few. Next slide. With all this information, this hybrid quantum balance is a leap forward in honoring our ethical responsibility. For all the Terminator fans watching this, it keeps people, not machines, at the heart of exploration. Instead of relying on opaque, purely quantum black boxes, hybrid systems bring in the best of both worlds and can partially tackle this problem. As you can see from the slide, they incorporate the fast AI decision making, but also create approaches and techniques which allow for human oversight and transparency, building trust between crew and AI, something that is essential in the isolation of deep space. So overall, hybrid quantum AI doesn't just promise better missions, it promises missions that are safer, fairer, and more sustainable. As an aspiring future astronaut, I believe that this is absolutely crucial. Expert research suggests that it keeps humanity in control, makes collaboration with every other computer decision, and that makes it smarter and more ethical. As we set our sights on our own moon or on the red surface of Mars and beyond, let us choose a future where advanced AI empowers astronauts, not replaces them. In the end, this internship underseas and the mentorship of Miss Bridget Kimsey was amazing, and it brought me a really enjoyable research experience, opening my eyes to an innovative opportunity that is artificial intelligence. Let us invest more research into hybrid quantum AI because this is a technology potentially designed not just for success, but for stewardship, ease, safety, and shared discovery.
And here we want to say thank you. Thank you so much to Architecting AI for space travel, this opportunity, to NASA, to the NASA SEAS program, to CSR, and I'll have the whole team join in. Thank you, thank you, thank you.
Thank you.
Thank you.
Thank you.
And thank you for watching. And if you have any questions, please let us know. Have a great day. Thank you.